beginning, when I started my postdoctoral research, started focusing on organic contaminants and focusing on contaminants that are commonly found in surface waters around the world, and yes, including Fountain Creek, as the topic of this talk will be. So what are organic contaminants? A lot of times we hear the term organic, we think about good things, organic foods, organic crops that are being grown. In this case, organic is referring to the chemistry of the contaminants. And there's a lot of different terminology out there that has been applied to grouping these compounds together. Emerging contaminants is one that's fairly all-inclusive. Pharmaceuticals, personal care products is another one. The last two of the acronyms listed up there, organic wastewater contaminants, OWCs, and anthropogenic waste indicators are ones that I've used. And recently I've gone to using a grouping that's a little more general, at least I think so, in anthropogenic organic contaminants. So you're going to see AOCs on a few of these slides. What are these compounds? And they are quite varied. They can be things like industrial compounds, things like fire retardants that are added to a variety of products, including the seat cushions that everybody is sitting on. We can be talking about agricultural sources of these contaminants. Of course, pesticides would probably be the thing that comes to mind first, but also veterinary pharmaceuticals are becoming quite a study area in recent years. Of course, in medical treatment for humans, we're talking about pharmaceuticals. We take pharmaceuticals in, we put pharmaceuticals out. Sometimes it's not 100% in, 100% out, but there is generally some fraction that leaves the human body unmetabolized. Household items. How many of you guys buy antibacterial soaps? It's almost hard not to buy antibacterial soaps these days. Well, if you look at the back of that packaging, chances are that you're going to find something called triclosan listed as the active ingredient. And it's a broad-band or broad-spectrum antimicrobial agent. Well, it shows up in a lot of places in the environment. We could also be looking at things of convenience such as plastic bottles that have plasticizers, phthalates, bisphenol A, things of that nature that do end up in the environment as well. And then I'm also going to group PAHs in this group. These are combustion byproducts, so hence the picture of the smoggy or area with all the vehicles there. It's a bit of an extreme example. So a lot of my research has focused on wastewater as kind of a conduit that many of these organic contaminants pass through on their way into the environment, and certainly on their way into surface waters. But I want to say that I'm not trying to pick on wastewater, it just happens to be that conduit to which they go through. We all contribute to what is going into the waste stream, so we're all responsible for these compounds entering the environment. Just to put some numbers to how much wastewater we generate in the U.S., on average, we are responsible for 450 liters of wastewater on a daily basis. And some small fraction of that is not liquids, but solids, about 240 kilograms of dry solids per million liters of wastewater generated. What we do know is that organic contaminants are not completely removed during wastewater treatment. Okay? And to illustrate this, there have been a number of studies focused on different wastewater treatment technologies, and a paper published in '98 showed that for pharmaceuticals, anywhere from about 10% was removed to 100%. Well, wait a minute, I just said that incompletely removed, but 100% suggests that they're completely removed. Well, that's on the liquid side of things. But we also have to consider that wastewater treatment plants also produce solids. So in most cases where you're looking at the high rate of removal of organic contaminants, that means that they're ending up in sewage sludge. And that's illustrated by another study here, which shows that at various points during treatment process, we see drops in the concentration of a few pharmaceuticals listed here. And the last one that's there is activated sludge. Okay? So there's a drop associated with activated sludge treatment, and usually that means that, yeah, it's leaving the liquid phase and going to the solid phase. And this is a well-pronounced phenomenon. It doesn't just occur in wastewater treatment plants, but also something that you might observe in the environment as well, that organic contaminants will tend to partition into the solid phase. Another illustration of this fact, probably one of the most prominently cited references in relation to organic contaminants in waterways in the U.S. was published in 2002 by a group of authors with the USGS, where they looked at 139 streams across the United States, shown on the map there, and lo and behold, they found quite a variety, different concentrations of organic contaminants in waterways around the country. Now, you may remember 3 years ago, there was a bit of a to-do about pharmaceuticals and endocrine disrupting compounds, other organic contaminants, in drinking water in the United States. There was a series of AP articles that ran across the country illustrating this fact. Well, the group responsible for that information was based out of Nevada. Then they did measure trace quantities of quite a variety of organic contaminants showing up in some drinking water samples in the United States. So where does it go? So I have a couple of pictures of wastewater treatment plants. Things enter the wastewater treatment plant. Some fraction of them tend to leave. Where might they end up? Well, if we look at the aquatic side of things, and I'll try our little pointer here, see if I can get it in the right spot. And if we're talking about the aquatic side of things, as I will focus on today, it could end up in organisms, including plants, other organisms in a stream or river, but it can also end up in sediments. A lot of the research that I've done is focused on the solid side of things, and sewage sludge, if it meets regulatory requirements, can be classified as biosolids, and land applied as a good source of organic carbon, good source of plant nutrients, but also tends to include a number of organic contaminants as well. And some of the things that we've focused on have been terrestrial organisms such as earthworms. Lo and behold, you find a lot of the contaminants that are in biosolids that are applied to land will show up in earthworms. We've even done some work showing that some organic contaminants can transfer into crops. Okay. So this is, of course, as I would imagine most of you are aware, a representation of the Fountain Creek watershed, the focus of the work that most of the work that I'll be talking about today. And these are just some of the sites that we collected samples. And this is part of a larger program at the university to look at water quality. And up at the top here, the MC stands for Monument Creek, UF stands for Upper Fountain, and then when those two come together, we have the Lower Fountain running from Colorado Springs to Pueblo. I've had a few students who have worked on projects related to organic contaminants and sediments. Talk a little bit about how they go about measuring things. I won't spend much time here, but we use something called pressurized liquid extraction, where we can subject the sediment to high temperatures, high pressures, and it's fairly efficient at pulling those organic contaminants off the sediment so that we can measure it. And we use a couple of different instruments and different techniques depending on whether we're looking for pharmaceuticals or for other groups of contaminants in the sediment. So I'm going to show some data from what we call synoptic sampling. What that means is we sent out teams to the various locations in the Fountain Creek watershed that we were collecting the samples from, and they did it simultaneously or within a very short period of time. So we really get a snapshot of what's going on throughout the watershed all at one time. And so this is from one of my students, a relatively small number of organic contaminants that he was focusing on. But I want to bring your attention to a few of them. First of all, we have phenanthrene, let's see if we can get there, phenanthrene and benzoyl pyrene. These are examples of PAHs. These are things that can be derived from combustion byproducts. So it's not a big surprise that they show up in the environment. We're driving around, everybody is contributing, unless you got the new Nissan Leaf, to production of some of these PAHs. And they can get into a watershed via atmospheric deposition, or they can accumulate in an urban environment, and when we do have a precipitation event, those can be washed from that urban environment into a local waterway. Now, the two that show up right here, triclosan and bisphenol A, these are uniquely anthropogenic or man-made compounds. These aren't naturally occurring in the environment, and you can see that some of the highest concentrations of any of the compounds that we're looking for showed up, or were these two compounds. Again, triclosan is that antimicrobial agent that is commonly added to soaps that you buy, but I don't know if you'd be aware, but even some toothpaste contain it. Some plastics are impregnated with triclosan, even some clothing ends up in deodorant. So there's a lot of sources that can ultimately be released into the waste stream and into the environment. So this is just a small snippet of the data that was generated by the student, but I think illustrates the point that, yes, some of these things are in the sediment of Fountain Creek. Okay. Another student took a look at some pharmaceuticals, hence the different representation of the data. We have some antibiotics, we have an antidepressant, anti-epileptic drug among the list, as well as a pharmaceutical used in asthma treatment. And what we see in the upper fountain here is that all of them show up at least in one sample, and the two antibiotics and the antidepressant show up in all of the sediment samples that were collected in the upper fountain. See very similar results when we look at Monument Creek. Sulfenthoxazole that shows up right here, that is one of the antibiotics in the list. And then we look at the lower fountain. We have our one and only detection of our anti-epileptic drug, carbamazepine. But again, we see the other four pharmaceuticals showing up in the sediment samples. I want to transition really quick to, well, why care about that? If we look at the concentrations that were listed, they're fairly small concentrations. Do we really care about that? And so a very recent student of mine was working with microcosms. So this is our laboratory attempt at reproducing a natural environment. And in this case, we had 4-liter jars, and we put in 3 liters of water. We added triclosan and triclocarban, which is a very similar, chemically similar compound, as well as similar in function to triclosan, in that it's an antimicrobial agent added to a lot of similar products. And we put in some sediment, started out as clean sand. We put in some organisms. We used corbicula. We have anacris as an aquatic plant, and fathead minnows that were put into our microcosms. And we wanted to see, where does the triclosan and triclocarban end up after we let this go for 10 days. Now, we are trying to imitate a surface water that has a continual input of wastewater effluent. So what we did is we removed 1 liter of water, refreshed it with some additional water that had the same concentration, as the starting concentration of the triclosan and triclocarban, and we let this go for 10 days. So now why would we focus on sediment in Fountain Creek? Well, it's because things do tend to partition into sediments in aquatic environments when we're talking about organic contaminants. And we did see this in our microcosm system as well. And so you can see we had 100 nanograms of triclocarban, triclosan in one treatment. We had 250 nanograms per liter in the other. Well, how did we come up with these? These are based on data that are out there in the scientific literature, where we take a dilution of what's typically found in wastewater effluent. So this would represent a body of water that is 10% wastewater effluent, and the 250 nanograms per liter would represent a body of water that is 25% wastewater effluent, and that is a very realistic scenario. Okay, and that is typical of concentrations that have been measured in water as well. So then we have the concentration of both compounds in the sediment. they're not higher than necessarily than what was in the water. But if you look in the parentheses here, we have the mass fraction that showed up there, and we see that a good portion of the triclosan and triclocarban that entered that microcosm ended up in the sediment. Okay? Well, now let's look at some of the organisms. Okay? So Anacris. Anacris was very efficient at accumulating both triclosan and triclocarban, so we have bioaccumulation occurring. Not a huge fraction of the total amount of these compounds ended up in the plants just because there was a small mass of the plants in the system. If we look at the clams, triclocarban accumulated quite well in our corbicula, but triclosan didn't. Triclosan didn't accumulate very efficiently in the corbicula. We look at our fathead minnows, and yes, we do see some accumulation of both of these compounds in the fathead minnows. Okay. So quickly transition to summary. Okay. We do see anthropogenic organic contaminants in Fountain Creek sediment. Not a huge surprise. We do have urban and wastewater inputs into that environment. So based on the state of science, we know that we're going to see some of these compounds present. Many or most of the anthropogenic compounds that we monitored are certainly indicative of human activity. Population centers, input into the stream system, not a big surprise. We've also shown, and this has been demonstrated by many others, that once in an aquatic system, many of those contaminants can accumulate in the organisms present in that system. And I think the next natural question then is, well, does that have an effect on the organisms? And I think we're fortunate enough that we're going to have a talk during this panel that is going to address some of that. But I will state that the student that was working on the microcosm experiments also did some toxicology work with Cereodaphnia dubia, a little water fruit. And I can tell you that the concentrations of triclosan and triclocarban that we utilized in those microcosms were about 100-fold greater than the LC50 for water fleas, or for that Cereodaphnia dubia. So it can have an effect on organisms that are commonly found in aquatic systems.